Okay, so welcome back to diffusion and flow models. So since it's been a while, I'm going to briefly basically review what we have discussed so far. And also today's lecture will be kind of dense in terms of that we are going to see lots of the formulations. But the purpose that I'm showing all the formulations here is not to just explain all the formulations the line by line, but more about basically to explain how the things that we have discussed in this class are basically all the connected each other. So that's kind of the main part of today's lecture. And especially we are going to discuss how the DDIM, the sampling that we discussed last time, is also kind of connected with some kind of continuous time deformulation. So speaking to that, let's briefly remind what we have discussed before regarding the DDIM, the deterministic reversal process. So what we have seen last time is that we could basically use some the pre-trained the diffusion model, which was basically used for the DDPM desampling to make it kind of the DDIM, the deterministic desampling by changing the formulation like this. And based on that, we could basically have those kind of like 3 steps in terms like sampling the next one, the noise, the sample the xt minus 1 given the xt here. So you should be basically familiar with like this formulation at this point. So regarding this formulation, like let me start with this quiz. So yeah, so this is the case. We can make it this as kind of 0, making it deterministic. So based on this, now what we can do is that we can write the single line the expression of the xt, actually the xt in terms of the xt plus 1, right? And also the noise prediction of the from the xt plus 1, right? So let's first try to write the expression of the xt in terms of the xt plus 1 and all the kind of the coefficients and also the noise term here. We're gonna see this again at the end of like this lecture. Yeah, everyone should now get this answer, right? So the thing is that, yeah, this is literally just like one line of the code. So every time what you just need to do is that, I guess you already implement this in the first assignment, right? You could actually implement each of the update step in the DDIM the sampling with the single line, right? By just taking the previous noise sample, if we just compute all the things while involving the noise prediction here, then we can directly compute the xt here, right? So we're gonna see this formulation again in today's lecture. And so we are basically seeing some kind of the sort of more the general version of the diffusion models. We started our discussion from the DDPM and DDIM kind of sort of the more the general version of the diffusion models. And then even we started to see the same model in the continuous time domain. So in the continuous time domain, the same diffusion models could be represented, expressed as kind of the stochastic differential equation with the default SDE defined in this way by just defining this like f function here and also the g function here, the drift term and also the diffusion, the coefficients term. And the interesting thing was that given the hourly definition of default SDE, the corresponding reverse SDE could be derived into this form, while basically involving some kind of the score terms here. So that's also kind of thing. Once we define the default SDE, then we can also directly define the reverse SDE into this formulation. So this was kind of the key fact that we discussed last time. And since the score can be now computed with the epsilon the predictor, the noise predictor here, when you plug this in into the reverse SDE formulation, then now we can see that the reverse SDE can be rewritten into this formulation. Okay? So which means that now if we just like define our own the f function, the g function here, and then the reverse process becomes basically solving this like SDE formulation. So these are also things that we have discussed last time. And we basically have discussed some kind of the specific versions of diffusion models last time, the DDPM and also these SDE kind of the cases. So those are some special the cases of like this general form of the diffusion models. So this general form of the diffusion models are typically called the variational diffusion models or the diffusion, the probabilistic models. for those kind of cases, we could also define the diffusion models by defining our own the alpha function here and also the sigma function here. So this is kind of the another way that we can also define the diffusion models with the full the diffusion the distribution like this. Basically sampling the xt, the noise data point given the clean data point x0 here. So in this case, the only kind of the constraint that we had for the definition of the alpha function and the sigma function here is that we just need to basically define these two functions in a way that the signal to the noise ratio, the ratio between the alpha and the sigma becomes like monotonically decreases over time. So the meaning of basically having this SNR to be decreasing over time is that we are basically gradually adding the noise into the given the noise data point in a way that at the end it becomes one of the samples of the standard Gaussian distribution. So this basically means that if we can define any of some kind of the alpha and the sigma functions, basically satisfying this condition, so that can be basically another version of the diffusion models. So we discussed some special versions of like the alpha and the sigma functions, but actually it doesn't need to be that specific form. You can define any forms of the alpha and the sigma functions. And also the meaning of like basically defining the full the diffusion distribution into this way is that basically we can do the sampling of the xt into this way. So when you basically remember this formulation, what you can do is that the sampling the xt can be basically considered as basically sampling any of the clean data point x0 and also the standard numerical the sample the z here, and just taking the sort of the linear interpolation between these two, right? So this is exactly aligned with some kind of our definition of the fold the jump distribution, right? So when you define the jump distribution into this Gaussian form, the sampling the xt here basically becomes that we are taking any of the x0 here, and then taking the standard Gaussian sample, and then basically multiplying those kind of the coefficients and taking some kind of the sum of them, right? So please remember this. We are going to see this in the next lecture as well. So given this kind of the general form of the diffusion model with the full distribution, so what we have seen last time is that we can go like the back and forth in terms of that. Given the definition of the full process, the SDE, defining the f function, the g function, the question last time is that how we can also derive the corresponding the full distribution defined with the alpha and the sigma function. So given the f and the g function, now we could also derive these like alpha and the sigma function in this way, basically defining the diffusion models either into the form of the SDE or into the form of the full distribution like this. Or we could do the other way around. But based on the definition in the previous slide, given the full distribution, basically defined with the alpha and the sigma function, now we also could derive the f and the g function into this way. So those are basically the formulations that we have seen last time, right? So please also keep this in mind in terms of that, given the f and the g function, we can also derive these two, and we can go also the other way around. Given the full distribution, we can also derive the full SDE as well. So how exactly this like the full distribution and also the full SDE are defined for the special cases that we have seen last time? So for the SMLDD case, for this correlated the distribution for those kind of cases, what you can see is that when you take the sigma function as our kind of the parameter function, then the full distribution was defined with this the alpha and the sigma function. So this is kind of the given function, the usual defined function, right? And we just set the alpha function to be 1. This was the case. And given this alpha and the sigma d function, we could also say that the alpha and the g functions are like defined in this way, right? And for the DDPM case that you already implemented in the assignment 1, when the beta function is kind of the parameter function, then we could say that the alpha and the sigma function defining the full distribution now can be defined in this way. And also the full SDE actually becomes quite simple form. In terms of the f function becomes like the minus the half of the beta function, and the g function becomes the square root of the beta function, right? So these could be all derived based on the connection between the full distribution and the full SDE we have seen in these two slides. And as I said, like these are some kind of the two special cases of like defining the specific the form of the diffusion the probability model. And actually there are more. There are many more. We are not going to basically discuss all those kind of the cases. So you can see that there are like DDPM plus, like something else, like something. There are many other cases. So if you are also interested in some kind of the more the options, you can check out this paper. Yeah. And the thing is that one thing that is very confusing last time was that, as I said, there's no textbook for this topic. So for many of the formulations here, I'm just following the formulations in some of the recent papers. The problem is that all the papers are basically not using basically the consistent notations, which means that there are these kind of cases. Like, the alpha basically we have the introduced in the DDPM lecture are basically different with the alpha that we are basically using in the VDLM, the variational diffusion model the formulation. So those are some kind of the confusions, right? So I'm going to clarify here. So those are some kind of the definitions that we have seen for the DDPM case. Do you remember? So we had that once we define the beta function based on that, we define the alpha hat here. Basically, these are all the alpha that we have seen the DDPM, the slice are not related to the alpha, the function that we are seeing in the variational diffusion models. So we will need to clearly see how these are basically they connect each other. So the thing is that in the DDPM, the fault, the jump distribution was defined into this way, right? But in the definition of the variational diffusion model, this should be the alpha, the function in the variational diffusion models, right? And this should be sigma the squared in the variational diffusion models. So which means that actually the alpha that we have seen in the DDPM formulation has this connection, the square root of the alpha bar here becomes the alpha function in the VDM the formulation. And also the square root of the 1 minus the alpha bar is basically the same with the sigma function. So don't get confused with this kind of very confusing notations. So this is kind of the problems with the notations that we are using. But basically, yeah, we are now going to switch our discussion into the general version, the variational diffusion models, which means that we are now switching all the kind of the notations into this form, basically introducing like those, basically the variables here. So based on those kind of the mapping from the variables that we have seen in the DDPM case with the variational diffusion models, now what we can see is that we can basically rewrite all the things that we have seen in the previous lectures. In the DDPM, DDIM the case, especially for the DDIM, the deterministic the reverse process. Now the formulation of the XT can be seen as basically the alpha and the sigma functions. Those alpha and the sigma are basically not these things that we have seen in the DDPM case, but coming from the VDM, the variational diffusion model, the parameters here. So based on those parameters in the variational diffusion models, now we can see the XT can be basically written into this formulation. Nothing but just like changing the variables here, right? And also for the reverse SDE, we can also basically rewrite some part of the formulation in terms of basically the alpha and the sigma of the functions that we are using in the VDMD formulations. Okay. So those are some kind of the remarks. So please keep these formulations in mind. We're gonna get back to those formulations. So this is basically nothing but basically we are seeing the same the DDIM the sampling and also the same the reverse process the SDE based on the variables that we have seen. We have basically used to define the general form of the diffusion models, the diffusion the probability models. So we are going to keep using the alpha and the sigma functions in here. Okay. It is clear. So please keep this in mind. And one more basically very confusing thing might be is that I'm just going to introduce like one more variable, the lambda function here. So that's basically making even more the confusion here. But we want to get back to this, like why we are basically introducing this kind of the new variable here. So basically the meaning of this like lambda the function is basically nothing but the half of the log of the SNR. So this when we have this curl here, this was the SNR, right? So we can see that this lambda function is the half of the log of the SNR. So when you introduce the lambda function here, then we can also rewrite some part of the formulation. Basically, the G, this curl function can be also written into the form of the lambda function. So this means that when you introduce the lambda function here, then we can see basically the conversion from the full distribution into the full SDE into this formulation. Becomes basically simpler like this, right? The G function can be basically simplified into this way. So those are some kind of the basic things to discuss to this topic, actually. So if I just remind these things that we discussed last time, some of the key facts is that basically the diffusion process can be described using the SDE in the continuous time domain. So which means that now we can define a SDE for the diffusion process. And then the thing is that we can also derive the corresponding SDE for the reverse process based on the process deformulation. So those are kind of some key facts in the continuous time deformulations. And also the thing is that we start to see some kind of some more general version of the diffusion models, which we call the variational diffusion models, or sometimes it's also called the diffusion probabilistic models. And the cases, the SMLD and the DDPM, are basically the special cases of like this kind of general form, right? So these are those kind of the key facts. And also the key fact was that the full SDE can be basically derived from some kind of the definition of the full distribution. And also the other way can be also done by the conversion that we have seen in the previous slide. So are these clear? So those are some kind of some key connections between the continuous time deformulation and the discrete time deformulation. And also the more important thing is that for the diffusion, the model, the SDE deformulation, we can always find some kind of the corresponding the ODE formulation, which basically matches the same marginal distribution. So which means that we also have seen the DDIM case, which is kind of the generalization of the DDPM. So we also could see that how we can convert the reverse process of diffusion model into the deterministic desampling, right? So actually, this kind of the SE due to the ODE, the conversion, is kind of changing the stochastic sampling of the SDE into the deterministic sampling using the ODE. So in the SDE formulation, we are basically injecting some kind of the noise every time, right? Some stochastic. In the ODE formulation, there is no some kind of the some random noise, which means that we can make the reverse process to be deterministic. When we start from the kind of the same starting point, we're gonna always go to the same end point. So that's kind of the similar connection that we have seen from the DDPM, the DDIM case. We can basically convert the SDE into the corresponding the ODE in terms of that we can do the same kind of the sampling without basically involving any kind of stochastic in the sampling the process. So, which means that when you see the reverse diffusion process, actually we can conduct all those kind of degeneration process by solving the ODE formulation. So that's kind of the key idea in the diffusion models. So this was also the formulation that we have seen. So these kind of corresponding the ODEs is also typically called the probability flow the ODE. So this is the SDE formulation that we have seen for the reverse process, and then the corresponding the PFODE, they basically matching the same the marginal distribution is basically expressed into this way. Also having some very similar forms, right? The only difference is that now we're having the 1/2 here, and not having some kind of the and also not having the node term here, right? I think this should not be secured here. So this is some kind of the type. Yes, and also we have seen that the reverse SD can be basically written into the noise prediction term here, and also the same thing also can be applied into the PFOD here, right? So given this, basically what we can see is that for the hourly definition of the alpha and the sigma function here, so once we define the alpha function and the sigma functions in the form of the variational diffusion models, if we plug in those kind of the f function, the g function into the PFODE, then now it becomes that the reverse process becomes like solving this formulation, given the definition of the alpha and the sigma d functions. Okay. So now we can consider all those kind of the generation the process as basically solving the ODE formulation. So solving the ODE formulation basically means that every time, like given the xt, now what we can do is that we can compute the derivative of the xt, which means that we have some kind of the way to basically compute the velocity in the field. So given any kind of the point in the space, given the information of the xt and also the noise predictor, what we can do is that we can predict the velocity into this structure. We are having some kind of the information of the velocity field, but the thing is that this velocity computation involves some kind of the neural net prediction, right? So every time we just need to basically run the feed for the process of the neural network, right? But given this kind of the velocity field, what we just need to do is that from the starting point, which is the sample from the standard Gaussian, the distribution, we just need to find the trajectory over the space in terms of that where this point goes at the end of all the kind of the time domain, right? And the kind of the one of the naive way to obviously compute this kind of trajectory might be is that we are basically moving very small step every case, right? So every basically the point, what we just need to do is that we just compute the velocity. And that's why we're assuming this kind of some sort of the linearity of the velocity, we just like move a little bit into this direction and just compute the velocity again, and just goes moving a little bit again, right? With some kind of a very small steps. So this is the naive way, which is called the Euler method, in terms of solving the ODE, the formulations. So this is kind of similar to what you have done in the diffusion, the reverse process, right? But the key thing that we are discussing here is that we want to compute these kind of trajectories with some kind of the fewer number of the steps. And also the challenges that we are basically doing for the image generation is basically how we are going to achieve some kind of the good the image outputs with the fewer number of the steps, right? So that's kind of thing. So which means that by just computing the velocity just for the very few steps, how we are also going to compute some kind of those kind of trajectory like more the accurate ways. So that's kind of the key idea here. So that's also kind of the key idea in terms of that, how we are going to basically accelerate the reverse process of the diffusion models. And for that, actually, without seeing the ODE formulation that we are having, actually, there are quite many techniques that I guess some of you might be familiar with, like those kind of things. So if you took the ODE, basically the course in the math department, then you might be familiar with those kind of some kind of the techniques. So those are basically all the techniques in terms of then how we can basically compute those kind of the trajectories with the velocity field with the fewer the number of steps. But these are some more like the general method without basically leveraging any kind of the characteristics of the formulations. And the things that we are going to discuss for today is basically how we are going to basically understand some kind of the specific characteristics of this specific ODE formulation and make some kind of the more efficient solver for this ODE formulation. For this specific ODE formulation, not for some kind of the general ODE formulation. In terms of that, we can basically solve this ODE with a fewer number of steps in a more effective way. So that's kind of the main thing. So please keep this in mind. So this is the ODE formulation that we are going to solve, right? So you can see that this ODE formulation has some kind of structure in terms of that. Actually, this form of the ODE formulation is called the semi-linear, the first order ODE. In terms of that, this looks like some kind of the linear formulation, right? So basically, we have the xt here and some kind of the coefficient function here. So it looks like some linear function, right? So linear basically does not mean that this function is kind of linear, right? I mean, so we see it's kind of like the whole function is linear with respect to the xt here, right? So we're having xt and some kind of linear function, but this is actually not linear. This is called the semi-linear in terms of that we are having the non-linear term here, right? If we did not have like this part, then this would be perfect linear function, right? But since we have this like the noise prediction, this is neural network. obviously this would not be basically the linear function, right? This is basically having some kind of the non-linearity into the formulations. So this is kind of like, combining some kind of linear part and some kind of non-linear part here. So in terms of that, this is called some kind of semi-linear ODE deformulation. And we are going to see how we are going to how we can derive some kind of some dedicated solver for those specific form of the ODE formulations. In terms of that, we can basically solve this ODE in a like more effective way. But before we get into that, just in case that you are not basically familiar with ODE, I'd like to go with some kind of the basic things with the ODE. So as I said, this is kind of the form of the ODE that we are solving. Not exactly this, because we are also having the xt as kind of the input the parameters of the Q functions here, right? But let's start with some kind of this like even simpler form. Exactly the linear formulation, right? So as I said, the linear in terms of that this is kind of the function that we are going to obtain, right? And given this function, this whole formulation is kind of like this formulation is linear, and this is the first order of the derivatives, right? So let's think about this simple deformation and even simpler one. Let's assume that this qt term is basically 0. So we some completely linear function here. And let's also assume that easier case that the xt is basically always like non-negative, basically always the positive in this specific case. Then for this kind of the very simple the form of the ODE formulation, how we can find the function that satisfies this equation? Yes, but yes, we are going to take some kind of exponential function with the xt. But if we get into some more the details here, let's basically assume that the xt is basically non-zero, basically for all the t. Then we can basically divide each side by the one of the basically dividing by the xt here. Then you can see that this left-hand side can be simplified into the other way, right? Can you see? So we are having the 1 over the xt times the first derivative of the xt. And then this left-hand side can be basically simplified into the derivatives of the natural log of the xt, right? So if you basically take the derivatives, the log of the xt, then we get basically this, right? So in terms of that, we can see that by dividing both sides with the x by the xt, we can see that the left side actually becomes the derivatives of the log of the xt. Then what we can do is that we can simply just take the integral for the both sides and take the exponential term, right? Then you're going to see that actually the xt becomes those kind of the exponential the function with respect to the p function here. Make sense? Great. So yeah, I just like went all the things like quite fast, but let's see. Let's try yourself. So when you have like this simple form of the ODE minus 1 over 2 with the xt with some kind of the initial condition that the x0 is basically the 1. So since this is the case that we only define kind of the velocity field, we also need to have some kind of the starting point, right? So let's set that the starting point is kind of the when the x0 when the time is 0, let's say the x function becomes the 1. So given this initial condition, if we solve the xt, what's the xt? Can you try yourself? Did you all get the answer? It becomes like very simple, right? It's basically exponential of the minus 1 over 2 times xt, right? So yeah, for those kind of the simple form, now we can see how we can find the solution for the ODE, right? So we are basically getting into some kind of more the complex case. So we have seen this. Let's go into the general case, and let's go even more general case. The semi-linear deformulation. So this is exactly the formulation that we are basically tackling in the PF-ODE case. So this is kind of the non-linear term. We are having some kind of linear function here, right? So given this kind of formulation, how we can have some kind of the analytic the solution for this like the ODE, right? So that's the main purpose like with this discussion. why we can achieve use some kind of some numerical method. The easiest kind of the way to taking some numerical method is the Euler method, right? Just like moving, it's a very small step every time, right? But now what we are going to do is that we are going to try our best in terms of like deriving the analytic formulations in terms of that we can basically achieve some kind of the better results with the fewer number of steps. For these like semi-linear formulations, what we are going to do is that we are going to leverage this fact. So this is basically the solution of this like simple form that we have seen in the previous slide. So here to derive the analytic formulations for this like degenerate case, what we are going to do is that we are going to use some kind of the very well-known, some kind of clever technique, which is called the exponential integrator. So this is the formulation that we are going to solve, right? To solve this, what we are going to do is that I'm going to just briefly introduce this kind of the new function, which is called the integrating factor, which is basically the function that basically become the solution of like this ODE formulation. Don't ask me why we introduced this function for now, because we're gonna get the reason very soon. So let's first define this like the new function that becomes basically the solution of like this ODE formulation. And in the previous slide, we have seen that the solution of like this formulation becomes like this term, right? So we're having some kind of exponential function here, right? So the reason like why we are basically introducing this like integrating factor is that once we define this like the mu function, let's basically simply multiply the both sides by this integrating factor. Having the mu term here, and the mu term here. And based on the product rule of the differentiation that we know here, then now we can see how this like left-hand side can be also simplified, right? Can you guess like how this left-hand side can be simplified in this case? So remember that the mu function is basically the solution of like this ODE. The derivative of the mu function becomes like this term. And based on this product rule, how we can simplify this left-hand side? You can see that this left-hand side, the whole left-hand side becomes like derivative like some function, right? So we can see that actually the whole left-hand side can be now simplified into the derivative of the product of like these two functions, right? Because the derivative of the mu function was by definition then we defined that becomes the this term, and this is the derivative of the xt. And from the product rules, then we can see that the left-hand side simplified into this way. So that's why we are basically introducing the mu function to simplify the formulation into this way. Then the rest of the thing is kind of the more like the straightforward. That is exactly the same thing. We're just taking the integral for the both sides, and also then when we say that actually the mu function is basically the non-negative, so even a positive, then we can also divide all the things into by the mu t. So you can see that we can also easily derive some kind of the analytic solution for the semi-linear, the first order semi-linear ODE formulation. So we are going to basically leverage this fact in terms of basically introducing some kind of the more efficient ODE solver for the PF ODE formulation. So the only remaining thing is that we just need to plug in this hourly definition of the mu function here, right? Then it becomes like quite complicated like this, like having all the kind of exponential terms. The good thing is that we can simplify this further in terms of that they are basically sharing the same base of the integral here. So by just simplifying all the things, now we can see that this becomes basically the analytic formulation of the semi-linear ODE. So given some kind of the starting point of the S here, so this is kind of the initial point, right? So this will be some kind of the some initial value, the starting point starting from the S, right? So this is kind of the given information. So given this kind of the XS, basically we can now compute the XT by computing those kind of the integral terms here, right? Make sense? So while basically this looks kind of complicated, like what we also do is that given the kind of the exponential integrator that we have seen in the previous slide, now we can basically just like derive some kind of the analytic form of the any of the first order, the semilinear, the ODE, the formulations. So keep this in mind, might be kind of complicated. So if we do one thing more, then let's also see some kind of the more the complex case. So now we have the, this is still kind of the constant with respect to the xt, right? But when you have some kind of like so offset term here, and with some kind of same the initial condition, can you also derive the xt satisfying this formulation? Let's try this. Is the same with what you get. I just like plugged in all the things into the formulation that we have seen, and these are canceled out, and we can say that actually the xt becomes like this simple form, right? So in this like short amount of time, you got some kind of the basic idea in terms of like how we can deal some kind of the analytic solutions for some simple the ODE formulation, right? So here, basically, the key thing is that not in the kind of the sort of the math perspective, but in the some computer science perspective, what we can basically do is that whatever the ODE that we have, we can basically use some kind of the some numerical the approaches. We don't care like what sort of the ODE formations do we have. The simplest kind of way, as I said, is that basically every time while basically assuming some kind of linearity, we just like move a little bit and just like go there and just compute the velocity again and just move a little bit again. So that can be kind of the simplest way that we can basically compute the trajectory, right? The thing is that if we want to basically compute the trajectory like, like more accurate way, we will need lots of the steps, right? As we also have some kind of the very complex some kind of the trajectory, as the trajectory is basically not straight. The thing is that if all the trajectories are basically straight, then how many steps do we need? We just need one step, right? From the very starting the point to the end point, if that the trajectory is just like straight line, then what we just need is the velocity at the beginning point, right? You just go straight until the end point. So that's kind of thing. In terms of solving the ODE formulation, if we basically want to get some kind of the accurate the results of the computation with the very fewer number of steps, the key thing is that we just need to make all the trajectories to be straight as much as possible. So that's the thing. But we don't know for the diffusion models that we trained, how much those kind of the velocity field that we are getting with the ODE formulation would be, how much that would be straight, right? So in terms of that, especially for some kind of all the kind of the very curvy trajectories, we will need to have some kind of the lots of steps to get some kind of the accurate the prediction of the trajectory and also get some kind of the accurate outputs for the at the end. So that's kind of the same with like what we have seen in the DDPM case. It should be the same because DDPM is kind of some kind of discretization in the case of the SDE formulation. So also in the DDPM, we need to have some kind of the lots of the steps to get some kind of the accurate outputs, right? The same thing in the ODE formulations as well. And there are some kind of the many well-known techniques in the numerical approaches in terms of that whatever the ODE formulation that we have, how we can basically get some kind of the accurate kind of the trajectories with the fewer number of steps. So you can basically consider using those kind of some kind of the techniques in terms of reducing the number of steps. But those are basically all the techniques that are basically not using any kind of the information or some characteristics of the specific ODE formulation. And what we are aiming here is that we are going to basically consider the characteristics of the ODE formulation, the PF-ODE formulation that we are seeing, which is having this kind of the first over the semi-linear structure. And based on the observation of like this structure, how we are going to see some kind of the more the effective way to solve this like ODE formulation by somehow deriving some kind of the analytic deformations as much as possible. So that's the basic idea. So if we get back to this formulation, the PF-ODE formulation that we have seen in the previous slide, as I said, like this is the semi-linear kind of things. We are having the P function here and the Q function here. So this is the nonlinear term. Nonlinear because for that we are involving the noise prediction here, right? So this is the only nonlinear terms here, the neural network. And then anything else is basically some kind of the coefficients that we are defining. So these are basically all the functions that we defined, right? So we can basically, so these are some kind of the given functions, right? So based on that, when you basically compute the exponential of the p function in this way, then we can see that actually this formulation can be simplified into this way. So still we have some kind of the linear terms here, which is kind of some concept some kind of the user-defined functions and having those functions. So the thing is that this is already kind of quite simplified, right? In terms of that we have just like the noise prediction here and some kind of terms here. One kind of the key idea here is that we are going to further simplify this by reparameterizing the integral terms here. So this basically shows the reason basically why we are introducing the lambda function here, which was the half of the log of the SNL. Here the key idea is that now we are going to, so this, the integral part was basically parameterized with the time t, right? But instead of like basically seeing the time t, what we are going to see is that this lambda was basically the half of the log SNR, which is basically monotonically decreasing function, which means that there are some kind of the one-to-one correspondence from the lambda, the value, into the time t here. So which means that there are some kind of there is basically some inverse function from the time t. So there's the function from the t to the lambda and also the inverse function from the lambda to t as well. So based on this fact, what we are going to do is that in terms like further simplifying the second part here, we are going to basically reparameterize this whole function, not based on the time t here. Here is written into tau here, basically reparameterizing into the lambda here, which is the half of the log SNR. The effect of that is that now we can basically cancel this out because we basically coming back to becomes the identity function, right? So based on that, we can see that actually that the complex, the ODE formulation for the reverse process became simplified into this way. So this is the case that basically showing that how we can compute the xt from any given the initial point of the xs. Which means that once we basically have some kind of the initial value at the time s here, then now we can compute the xt by solving this formulation. And this is basically only involving some kind of the integration of the noise prediction, while basically simply weighting this term into some exponential term here. So this is also kind of the given function, just like weighting the noise prediction and just taking the integral of the noise prediction. So the meaning of like this is that we are basically deriving some kind of the analytic formulation, like solving the ODE in terms of that we only have like this part. So this is basically the only part that we still need to solve in a kind of numerical way, because like this is involving the noise prediction. It's basically neural net prediction, right? So still there is some kind of the parts that we need to leverage some kind of the numerical method in terms of computing the integral. But we are simplifying the part that we are involving some kind of the numerical method in terms of only taking the integral of like those parts. So in terms of that, we can get some kind of the accurate computation for the linear part, and was only remaining this like the nonlinear part in terms of involving some the numerical method. And the idea in terms of like somehow involving some the numerical method for this integration is also quite simple. What you can basically assume is that it's basically nothing but just taking the integral like this kind of noise prediction with some kind of the weight here, right? How can we basically do some kind of achieve some kind of approximation for this? Basically, this is basically nothing but you can think that this is taking the integral of the noise term over time, which is now parameterized into the lambda, but basically it's like taking the integral over time with some kind of the weight term here, right? So basically the one way that we can simply approximate this is that we are basically assuming this noise prediction function as kind of the piecewise linear. So some certain range of the time, we're going to assume that this noise prediction becomes some kind of the constant. So this is like coming back to the what we have done in the reverse deep process sampling. So what you have done in the first assignment was basically define some kind of the time interval, right? From the 0 to the capital T, you somehow define the time interval, and basically updating the xt over time, right? Starting from the x capital T, going all the way to the x0, basically updating the xt over time, right? And what we are going to do is that we are going to do kind of the same thing in terms of like dividing the time domain into the multiple the intervals. And what we are going to do is that we are going to assume that this epsilon function is basically the constant for each of the interval. Make sense? So which means that when you basically compute the next sample, sorry, this should be xt plus 1. So there's some typos here. So when you compute the xt given from the xt plus 1, we are going to assume that this noise term that we are computing from the xt plus 1 becomes constant in this interval. And with this simple, basically the assumption, the approximation, now we can compute this like the analytic deform of like these whole deformations. Make sense? This is the case that we are assuming that those interval is basically the noise term is basically constant over the interval, and the only thing is that we just need to compute these integral terms, right? So this is like the things. So let's recall that in how we define the lambda function here, right? So based on the definition of like the lambda function here, can you compute this? Can you rewrite this formulation into the alpha and the sigma that we have seen in the VDMD case? This will be last quiz today. Did you see this? So the exponential term basically can be simplified into this way. Just like simple calculation, right? But based on this simple calculation, what we can see is that kind of surprisingly, if you plug in this the formulation here into this part here, then we come back to this formulation. Do you remember where we have seen this before? If you don't remember, I recommend you to check all the slides again. But this is exactly the formulation of the DDIM, the deterministic sampling. So we basically replace some kind of terms with the alpha and the sigma function that we are using in the VDM deformations, right? So it turns out that what we can see is that this is kind of the another way that we can basically interpret the DDIM, the deterministic desampling. So actually, it turns out that the DDIM, the deterministic sampling, was the first order the discretization of the ODE formulation. But not just directly discretizing the entirety of the ODE formulation, but just like leveraging the semilinear structure in terms of that we are taking the exact the solution for the linear part. We only basically do some kind of the first order approximation for the nonlinear part, which is the noise prediction part, right? So we have seen that what we are doing for in terms of the approximation here is that we could do the first order approximation for the entire ODE. But what we are doing is that we only take the approximation for this like second part, this part, right? In terms of the assuming some kind of the piecewise linearity for this like noise prediction, right? So by just taking only the numerical the computation for the nonlinear part with the first order approximation, what we can see is that actually the DDIM, the reverse process, the deterministic process turns out to be the first order discretization of the ODE deformations based on the semilinear structures. Right? So that's kind of the interesting point. We can basically see the same basically the generation process from the different the perspectives. We can see that the same thing which can be interpreted as kind of the first order kind of the approximation of in the continuous time, right? And the reason why we could achieve some kind of the good results with DDIM desampling was that basically this is kind of the case that we are analytically integrating the linear part and only approximating the nonlinear parts. So that's basically the reason that we can typically achieve some kind of the quite high accuracy with the fewer number of steps with the DDIM sampling, because it becomes like much more accurate, the approximations compared to the general case that we are using the ODE solvers for the entire ODE formulations. And the good thing of like having this interpretation of the DDIM sampling based on the continuous time domain here is that, as I said, DDIM is basically approximating this formulation, right? And we just like did some kind of the first order approximation. And what if we do the second order approximation and the third order approximation? So that would be kind of the even better way in terms of like achieving the higher accuracy. How about the second order approximation? So roughly speaking, the very basic idea in terms of achieving the second order approximation is that for the given the time domain, the time interval, we are going to split each of the time interval and basically first performing the first order approximation by computing the middle point here. So now we are basically not computing the next sample for the entire time interval, but just like half of the time interval, just computing the U here. And based on that, we are basically do the second time the update, basically updating the noise prediction with the middle point, and based on that, we compute the final the data point. So that becomes some kind of the basic idea for the second order approximation. And can you also do the third order approximation and the first order approximation? Yes, we can see how we can do this kind of the things in the recursive way, right? So that's kind of the good thing in terms of that we are having some kind of the different perspectives of the DDIM, the sampling into the continuous time domain, which means that also with some kind of even fewer number of steps, by just like approximating those kind of trajectories into the second order or the third order, for the same number of the steps, we can get some kind of the even more the accurate results. So this is kind of the comparison, like DDPM is basically here. So with some kind of fewer number of steps, the FID is like very high, which is basically not very accurate kind of computation. So as I said, DDIM is kind of the same with the DDIM, the solver one. Solver one basically means the first order approximation. So it goes down to here. So with some kind of the fewer number of steps, now we can get some quite accurate results. If we basically go into the higher order, into the second order approximation or the third order approximation, then what you can see is that even with the 15 steps, so this kind of dot line is basically here, kind of the accuracy that we can achieve with some kind of the 1,000 steps with the DDPM, the DDIM, and the sampling. Even for the 15 steps, we can achieve some kind of the same number of some kind of the outputs, the same accuracy here, right? So that's kind of the power in terms of basically understanding all those kind of the diffusion, the process in the continuous time domain. When you see basically the SDE to the ODE conversion, and basically find some kind of the better way to solve the ODE formulation, even with some kind of the fewer number of steps. And as I keep saying in this class, this is also quite interesting, the point in terms of that this is like all done with the same pre-trained model. You don't need to retrain any kind of the new model. Using the same trained model, only at the inference time, by just changing the formulation that you are performing the reversibility process, with some kind of the better understanding for the ODE formulation that we are solving, by just introducing some kind of better solver, with the much fewer number of steps, we can even get some kind of the better results like this. So that's kind of some interesting aspect of the diffusion models in terms of the different perspectives of the understanding diffusion models can provide some kind of the better way to achieve some kind of better results with the fewer number of steps. So this is kind of the very basic idea in terms of basically introducing some kind of the dedicated ODE solver for these like PF-ODE formulations. And there are many more in terms of like how we can also introduce some kind of the better ODE solvers for the same ODE formulations. So if you are more interested into the more deeper things, more like mathematical kind of things, I recommend you to check this out, to check out those kind of the papers. Okay, any questions? So as I said, like today's lecture was kind of dense with lots of the formulations. I strongly recommend you to basically check out those formulations not just like understanding line by line, but basically, more about like understanding how those things are basically connect to each other. So that's quite important things in terms of like understanding diffusion model.